Welcome to the second iteration of the My Robot demo. We are showcasing an Android app that controls and communicates with a ROS-based car robot for SLAM and autonomous navigation. This video shows a robot acting as a delivery vehicle that communicates with two distinct users. Before you are the screens of three cell phones, that of the robot as well as two users on the Slack messaging app. One user will message the robot to pick up from another user at a specific location. The robot receives the message and handles it in a natural language processor to give an appropriate response, as well as to send the robot the proper commands and parameters. As you can see, the user messaged the robot to pick up from Ahmed, a Slack user, at a predetermined location. The robot will now go into autonomous navigation mode to perform its task. The robot relies on the robotics operating system and its open source navigation packages to autonomously navigate to its goal. Once the robot reaches its destination, it messages the second user. The second user can then drop an item on the robot, in this case a small piece of candy, hit the job delivered button on the screen, and wait for his picture to be taken. The robot then sends the image to the first user as confirmation for delivery. The second user will now command the robot to deliver the candy to another location to a certain user, and the process is repeated. It is necessary to note that all the location coordinates are stored in a dictionary on the robot. So in summary, the app has access to cell phone capabilities like the natural language processor, allowing the robot to understand user input, and the Slack API for access to social media, while ROS enables us to easily create complex robots due to its many open source packages. It didn't send me a message yet. Where is it? Oh, do it!
How to take a picture?
It's taking a picture?
Yep, it is. Seems
That's it?
Yeah, that's it.
The navigation stack has a global cost map and a local cost map. The local one is smaller in size, surrounds the immediate vicinity of the robot, and is updated more frequently. The robot uses the local cost map to avoid obstacles, as you can see. The stored map on the robot was obtained through simultaneous localization and mapping. As you can see on the screen, as the robot moves, it uses the LiDAR sensor as well as a ROS SLAM package to build an occupancy grid of its surroundings. This is how we build the maps used for the navigation stack. The SLAM package works beautifully, but the navigation stack unfortunately does not. Whilst the robot can in most cases go from point A to point B without any intervention whatsoever, it is not very robust. That is mainly due to the limitations of the Raspberry Pi. Future improvements can be made through code optimization and better load handling. This video only shows what the robot can do. For a much more detailed look at our work, please refer to our GitHub repository linked below. Furthermore, this demo is based on a previous project, which was also done with Android and ROS, in which the robot was tasked with identifying tennis balls using the OpenCV library. The link for this project's repository can also be found in the description below. Thank you all for watching.